Thank you for joining us for today's webinar, The Science of the Concrete Surface. We have some brief housekeeping before we start. Your phones are muted. If you have any questions, please type them into the Q&A box in the corner of your screen, and we'll answer them at the end of today's session, time permitting, or via an email after. And you can always send your questions to mapeidigital@mapei.com. We also invite you to visit the floor covering and installation systems page on our website, www.mapei.com, where we have videos, projects, downloads, and more all about adhesives and flooring solutions. It's a lot of information, and it all happens to be overseen by today's speaker, the business manager for MAPEI's floor covering and installation systems product line, Jeff Johnson. Jeff brings to the industry more than 35 years experience in the development and marketing of floor covering installation products. His practical experience in the construction industry and as a bench chemist give him an insightful perspective on surface preparation, moisture mitigation, and floor covering installation. Today, he's going to share information about concrete and, among other things, how adhesives change the chemical balance of concrete surface. So, without further delay, Jeff, the floor is yours.
Thank you, Jen, and welcome everyone. And thank you all for taking a little bit of time out of your extremely busy schedules to follow along with me as we talk a little bit about the science of the concrete substrate, the surface that we all have to deal with when we're installing floor covering on top of them. So let's get into the subject, and if you have any questions, by all means, save them towards the end, and we'll have some opportunity for a little bit of Q&A at the end. What we are going to be talking about today is, I hate to do this to you, a little bit of a chemistry class. I've always been very interested in the chemistry of what's going on. That's my background, and I'll be quite honest with you, this whole presentation has been based on my question in my own mind is, you know, what do we get when we do moisture testing on concrete, and why does the glue turn to goo underneath the floor? What's the driving factors that really make that stuff happen? And what this is going to talk about today are my theory or hypothesis and some of the science about what's going on. So we're going to review some things here. We're going to take a look at the basic principles of pH values. That's very important for what we're going to talk about. And there's some things I want you to get out of it towards the end of the presentation that are very important about that test. We're going to spend some time talking about the chemical composition and curing of concrete and cement. I mean, that's the more you know about the canvas on which you paint, the more you know about the concrete on which you install the floor covering, the better educated you're going to be on how to pick the right products for any given installation, how to avoid problems, and so on and so forth. We're going to talk a little bit about the process of carbonization. It's not what we're talking about fossils here. We're not going to take you back to the pre-carbon era, whatever it was, and learn about fossil development, but we're going to talk about the carbonization of a concrete surface. We're going to discuss osmosis and how this is relative to a concrete slab. Sometimes I refer this to as a salt pump, but it's very important to understand what goes on the actual chemistry and physics of a concrete surface and what it can do to an adhesive and a floor covering installation. We're going to talk a little bit about the proposed mechanism for moisture generation under flooring installations due to that osmotic activity. And again, I think discuss techniques and practices to avoid moisture-related failures. Again, a lot of this stuff is based on me asking the question, well, where did the goo come from? And why did this happen? And what does this really tell me? And how do I avoid this in the future? So hopefully that fits with some of the things you'd like to hear about and learn about. And again, if you have any questions, by all means, save them to the last, and I'll do my best to answer them. Okay. So Let's start off with a kind of a dumb rhetorical question. Is it stone or concrete? I mean, it sounds silly, but the two are very similar products in some respects. They're both very hard, they're both very durable, but the two are made in considerably different aspects. Now, we would love to be able to build on stone, and some of our ancestors built on nothing but stone, carve it with hand and chisel it out, and that's what you walked on, leaned on, and what protected you from the rains and the elements on the outside. But how was that made? Obviously, it's a natural process over billions of years and very high pressures and temperatures, and you wind up with granite or marble or whatever else you have, but they're all stone. Concrete, what you might consider synthetic stone. It has many of the same properties. It's very strong. It has compression strengths that can get up to 6,000, 7,000 PSI, where stone's in the 12,000 to 16,000 PSI. They're hard. They've got similar Mohs hardness scales, but they're put together considerably different. Concrete is the result of a chemical experiment, a chemical reaction, if you will, where water is added to some chemicals along with some aggregates, and over time it crystallizes and makes a synthetic stone. But that's about where the difference, the similarities will end, okay? I'm going to go back and we're going to spend a little bit of time talking about testing the health of a concrete slab, or the things that are relative, or things that we currently use, if you will, to test a concrete slab for the stuff that we think is important for us as a floor covering installer. And if, again, I'm preaching to the crowd here at this point, I think everybody understands what those tests are, but according to ASTM test methods or test requirements for resilient flooring, I'll go for that, Mark. There are three tests that are pretty important. The ASTM F-1869, that's the moisture vapor transmission rate test. We have a relative humidity test, which is the ASTM F-2170, and the pH test, which is included in the ASTM F-710 documents. Again, for those of you who are on the webinar today who are involved in this industry, if you do not have copies of these, I highly recommend you get the current one from the ASTM website. They are copyrighted and owned by whoever pays for them. Something I can't just share with you, but you can go and buy your own copies yourself. Something to have in your document library. It's very important because all the procedures and the requirements and interpretation results are in those documents. So let's spend a little bit of time, if you will, with me explaining what these tests are, what they do, what they report, and how is that relative. So the first one we talk about is the ASTM F-1869, the calcium chloride test kit of infamous renown. What does that measure? That measures the rate at which moisture is leaving a concrete slab. It's all and that number is reported in a number of pounds of moisture leaving a concrete slab over a 24-hour period, extrapolated over 1,000 square feet of surface area. Okay, so again, this is the test that was been around forever, probably followed the rubber mat test or some other things, but this is a way to quantify the rate at which water is leaving the system. Okay, so again, what does that really mean? That tells you how much water is evaporating over the slab, out of the slab over a period of 1,000 square feet. So we all come up with numbers. From the days of old, it used to be, you can't install anything that had anything more than 3 pounds of water vapor leaving the system over a period of 24 hours. Raise your hands as to when was the last time you've seen a 3-pound concrete slab. I don't think in my 35 years, I don't think I've ever seen one of them. But it does give you an idea of the rate. Now, obviously, that theoretically is going to change Over time, as the water starts to leave the system, the rate will slow down, and so on and so forth. Here's what's, I think, kind of an interesting thing. Has anybody really thought about what does that mean? Is that a big number? Is that a small number? Is it, what does it really mean? So if you take a look at the concrete slab extrapolated that you're trying to deal with, 1,000 square feet of concrete at a 6-inch depth is equivalent to, if my math is correct, of 55 cubic yards of concrete. That's a lot of concrete. 1 yard of concrete at a 0.5 water to cement ratio will have 235s of water as part of the mix. So 55 yards of concrete will therefore have 13,055 gallons of water in it. If you divide that, that's a lot of water. That's a pretty good swimming pool of water. And about 45% of that water is put into the system to help move it around, make it fluid, get it to be able to place, and also means that it's available to evaporate. Or half of that number is 5,875 pounds will have to leave through evaporation, or wick out or go somewhere else. But that's something that I've never really thought about, and then you might have some consideration. So if a concrete slab has tested according to the ASTM F-1869 at a rate of 25 pounds per day in a 24-hour period, it's going to take 235 days for all that moisture to leave. And I think we've all seen a variety of different charts about how concrete dries and what the rate of evaporation is and why it takes, what's the number? I think it was 72 to 80 some days of curing to get it down to an 8-pound level, but quite a long time for a concrete slab to get to complete dryness. And it's really something that's never really going to get to that completely dry phase. It's always leaving. So a little bit of trivia for you in terms of what to think about, but I've always wanted to know, and I'm curious minds, what does that mean to have a 25-pound rate of evaporation coming off a concrete slab? And what does that really mean in terms of how much water is really there? So now you all know a little bit about what that means. Now, what's also important to note about the moisture vapor emission rate information is that once you cover it with an impervious moisture material, whether that be an epoxy membrane, whether that be a vinyl sheet flooring, something that's non-breathable, or even tile, resilient tile products for the most part, once you start covering it with an impervious moisture vapor barrier or impervious floor covering material, you basically turn off the valve on the evaporation rate. That should be quite simple to you. And at that point, the MVER becomes irrelevant at some point. It no longer has an opportunity to evaporate into the atmosphere. Okay. Having said that, on the other hand, things that are porous or absorptive, like carpet or wood, will allow the slab to continue to breathe. But impervious floor covering is like closing the window on the outside. The humidity on the outside is going to remain on the outside. Porous floor coverings like wood or carpet are like closing the screen, slowing down some of the movement of the vapor from the concrete, which in this analogy is the outside humidity, to move through it as well. So something to keep in mind as well. I do want to address some mythology that I've heard numerous times in the field, and that is that the moisture vapor emission rate is a pressure. The difficulty, I guess the logic why people came up with this, that somebody says it's 25 pounds, a concrete slab, you get the feeling that we're talking about pressure, like air pressure going in a car tire. You fill your tire up to 25 pounds of pressure. This is not a PSI reading. Please do not construe that the moisture vapor emission rate is a pressure reading like PSI. It is a rate at which things are moving through a concrete slab. It has nothing to do with pressure. And things that are going to affect that rate, and obviously things that they've tried to address in the ASTM F-1869 standard, are things like the porosity of the concrete slab. That's why they want you to do this test on an area that has been ground or opened up, as opposed to something that's highly polished and finished, so you get an idea what's underneath it, which I always thought was kind of weird, because you're not going to grind the whole floor, you're going to install on the burnished concrete. But okay, that's the standard that allows you to get to a consistent surface to work with, because burnishing and polishing all comes up with different rates of porosity. And that's the second thing. Additives such as fly ash or silicate materials can also affect the porosity of the concrete slab. Fly ash particularly will make that surface very glass-like and will totally reduce the amount of water vapor evaporating out of a concrete slab, because the pores are much smaller and tighter. The ambient relative humidity is a big deal, and that's why the ASTM test method requires that you run this at 72 degrees Fahrenheit under controlled humidity as well, so you have some idea that that's all the same, and the temperature must be the same. And all these things are chemical reactions, and all of them are dependent on the temperature at the time. Again, lower temperature means lower chemical reactions, lower emissions, lower evaporations. Higher temperatures, on the other hand, will make things a lot faster. So something to think about. The other test that we perform on concrete slabs that's become very common and very important is the ASTM F-2170. This is the test that measures the amount of humidity contained in the concrete slab. And this one, I think, is becoming more relevant and more important to us in the floor covering industry, because it really tells us more about the state of a concrete slab, the condition inside that. But it's also important that you realize that the slabs that the probes that are used to measure the RH of a concrete slab, you have to know the depth of the concrete slab that you're working with, because it's supposed to be put into the concrete at a 40% of that total depth. So if it's a 4-inch, 5-inch, 6-inch, 8-inch, 12-inch concrete slab, you have to do a math calculation to figure out how deep your probes have to go in. That's a very important deal. Why is that important? Because what this test will tell you about the concrete slab is what is going to be the expected homogenized humidity of the concrete slab once you put an impervious floor covering on the top of it. So again, the concrete in its normal living condition, uncovered, that's open to the atmosphere and allowed to evaporate, it's definitely going to be a little bit drier on the top of it, and towards the bottom of it, it's supposed to be, if you're on top of an impervious moisture barrier, which every concrete slab is supposed to have, which we know it doesn't have, it's going to be a lot damper on the bottom. But as soon as I put something on the top of it to close it off, all of the humidity balances itself out. So the RH reading that you get in a concrete slab is supposed to be indicative of what it's going to be once you cover it with floor covering. I think that is really the more important one to deal with over time. And again, what would change that RH condition? Most oftentimes, the thing that's going to be the big deal about this is whether or not you had a moisture vapor barrier below the concrete slab or not. If you opened that up or poked some holes into it or didn't put one in place, then you're constant contact with the ground. And if the water table changes or if water comes from the outside, then you can certainly have some impact on the overall humidity in that concrete slab. Okay. All right. I don't know why this isn't okay. The last test we're going to talk about is, and probably the most important thing that we're going to spend more of the time with here, is to test of the pH of a concrete slab. And it's not really been talked about much, but I would like for you to put this more front of mind than back of mind. We do an awful lot of calcium chloride tests. We do an awful lot of RH tests. That's all great. And that does tell us some useful information. But I think the most important thing to deal with is what's on the surface and what is going on in terms of the overall pH again. So what are we doing here? We're testing for the presence of soluble chemical compounds on the surface. And I want to spend just a moment here to bring this to your attention. When we run a pH test, what do? We take some deionized water and drop it onto the concrete surface, and then either using a litmus paper or a pH probe, we catch the pH of that solution. What's going on? We're actually dissolving something off of that surface that gets into the water. Would you drink that water that was coming off a concrete slab? A dumb question, please don't do that. But the point that I'm making is that things are dissolving. If I put water on top of a slide, a window, a piece of glass, the pH is going to be unaffected. If I put a drop of water on a piece of metal, the pH is not going to be affected. It's not dissolving. So if I put water on a concrete slab and something is going into solution that I can record a pH of, what do you think's happening to a water-based glue when I put it on top of the concrete? Is it also dissolving what's on the concrete slab? And does that have some impact on the adhesive performance of going into the glue? The answer is hell yes. So we'll talk a little bit more about that and the reason why this is having some very important thing. So what does pH measure? And this is really kind of important for you all to remember that pH is a measurement of the concentration of hydrogen ions or hydroxide ions in solution. That's all it does. It's very specific and very important for that. Nothing else. No calcium ions, no sodium ions, no potassium ions, no sulfate ions, no chloride ions, nothing else but hydroxyl ions or hydrogen ions, acids or bases, okay? So in order to do this test, you've got to have water and some sort of water-soluble salt or acidic base. For example, calcium hydroxide or lime. Where does the lime come from in the particular situation? We'll talk about that. So that's very important. So what type of adhesive do you think might be the most sensitive to pH? Is it going to be an epoxy, a urethane, water-based adhesive like acrylic PSAs or an SBR latex stuff, modified silane, tape systems? Hopefully you've answered water-based because that's the correct term. They're going to be the most sensitive to the pH of a concrete slab because they have water in them. And the water is going to obviously helps disperse what was in the adhesive, but it's also going to dissolve what's on the surface of the concrete slab. So if you ever wanted to know why, we tell you to do not install on concrete slabs with water-based adhesives and pHs that are higher than 11 or 12. This is the reason, because the higher you get, and this is a logarithmic scale, it's pH of 7, a pH of 8 is 10 times higher, 10 times more higher, 10 times more higher. So it's a very high concentration of hydroxyl ions when you get into that pH of 12, 13 to 14. You know, it's the kind of stuff that will burn your skin. This is nothing to mess with. And I will remind you that concrete, wet concrete at a pH of 14 is super corrosive. And if you're not wearing proper protection while you're monkeying around with it, you'll wind up with some pretty significant burns on your hands, and they are painful. Trust me, I've been there and done that before. So anyway, it's very important to realize that a high pH concrete slab is not a good thing to be working with water-based adhesive. So what does the high pH tell you about a concrete slab? And really what you're measuring at this point in time, it's basically tell you how green it is or how young it is or whether or not there's been not enough process of carbonization on the surface of the concrete to neutralize it. So a green concrete, as I mentioned before, has a very high pH to get with it, and it hasn't had enough time to react with the carbon dioxide in the air to neutralize the surface. And we'll talk a little bit about carbonization here in a minute. And what that means is that surface has a high concentration of calcium oxide or calcium hydroxide, and so on. So the calcium hydroxide is a very important component of cement. And when it reacts with water, creates that calcium hydroxide, that's the lime portion, and that will result in a very high pH. And again, what are the risks of installing over a high pH slab? The addition of soluble salts to water-based adhesives can cause them to destabilize. And I know for any of those of you who have worked with SBR-based latex adhesives for the insulation of broadloom carpet, this high pH concrete slab is notorious for causing destabilization and that end result, like people say, it's balling and stringing underneath the trowel. Why is that happening? Is it because the high pH is dissolving into the adhesive mix, changing the pH of the adhesive itself, causing it to destabilize, and clunks out of solution, and you wind up with a mess on your hands. What does a neutral pH tell you about a concrete slab? So if you put your drops of water on a concrete slab and I'm still getting 7, which is neutral water, which is water, it tells you that there's something on a concrete slab that's inhibiting you from getting actually coming in contact with the pH, with the concrete itself. Things like sealers or coatings or curing compounds are something that you might not necessarily see. They're clear, generally speaking, but they're prohibiting that water from contacting the concrete. Guaranteed 100% of the time, if you have an open concrete surface and you drop water onto it, something's going to dissolve into there and you will get a resulting pH. If, on the other hand, you've got a coating on top of it, you will get that neutral pH. So what would I do if I had a neutral pH in a concrete slab? I would abrade it, try to remove some of the coating on top of it, and redo the pH test, and 9 times out of 10, you'll get something between 9 and 12. Okay, but that's important to know. So summarizing what this stuff is, and we're going to get into the science here in a minute. Hopefully this has been science and not mythology. Just to confirm, again, the moisture vapor transmission rate generates results that are the rate of moisture evaporation from the slab. And keep in mind that there is a lot of water in a concrete slab over an area of 1,000 square feet. That's going to take a long time to totally evaporate. So that 25-pound number should really tell you, wow, there's a lot of water in here. Even if it's 12 or 8, do the math, go back to yourself and go to that 6,000 pounds of water remaining. And if it's an 8-pound concrete slab, I can't even do it, 720 days before it to get dry. Sorry, my math is gone. Relative humidity tests will give you the state of a concrete slab once an impervious floor covering has been installed. Again, it's talking about what happens when you cap it. And the pH test is very focused on the fact that it tells you what is the amount of soluble calcium hydroxide remaining on the surface. But is that all that's on the surface? Let's take a little bit of discussion about what goes into making concrete. And for those of you who are on the phone, I'm sure many of you know quite a bit about this, maybe more than me, which is entirely possible. But just be aware that concrete is made out of cement to start with. Where does cement come from? It's from limestone, chalk, basically calcium carbonate combined with shale, which is the aluminum and the silicate part of it, with iron and silica sand and so on and so forth. All these things are put into a rotary kiln, turned and up to an incredible amount of heat, over 2,000 degrees Fahrenheit. And you create a thing called clinker. The clinker goes to the grinder, and that creates what we commonly know as Portland cement. So it's a very interesting, complicated chemical process, and creates a very hygroscopic material in the form of cement. It wants to go back and get into a more common state. So this is what comes out of that when that process is all done. When you go to the kiln, dry cement contains tricalcium silicates, dicalcium silicates, tricalcium aluminates, tetracalcium aluminoferrites, and the gypsum additives of calcium sulfate dihydrate. So I get points for saying those things properly without necessarily stumbling on the words. But this is the kind of the chemical stuff that goes into making cement. And all these things are the things that are going to react with moisture when we put them together and create concrete. So it's concrete. It begins with a pretty good chunk load of cement, and then we add aggregates, fine and coarse sand, and larger aggregates. And this is the stuff that we get to work with on our installing the floor covering. There are also some additives that go into the equation: water reducers, flow enhancers, set time controls to create a winter blend, to create a summer blend, freeze-thaw stability, porosity control. A variety of different bits of mummy dust go into creating a concrete slab. But the two main items are cement and aggregates and fine and coarse sand. So what happens when you mix the cement, water, and sand all together? And it becomes a very complicated and beautiful chemical reaction of things that happen. All of those silicates and the tricalcium and dicalcium silicates start reacting with the moisture, creating ettringite and calcium silicate hydrates, releasing calcium hydroxide. You're whipping in some air into the thing as well as a bunch of heat being generated as part of the process. So it's important to understand that this concrete, the two really important aspects of its strength and its ability to be that synthetic rock are the crystalline structures that are formed by the ettringite, which are the long spindly crystals, and the calcium silicate hydrates, which are the ones that really build the strength. And that's the shorter crystals, but they're more integrated. We kind of see some of the pictures of what they might look like in those electron scanning microscope stuff on the right. Okay. So once the concrete is placed, what do we do next to it? We start vibrating it, shaking it, and working it into a flat surface, steel troweling it, bull floating it, whatever you want to call it, to get it into a smooth finished surface that which we're going to have to put our floor covering on it. That finishing process brings the bleed water to the surface. And what is the bleed water? It's that water of convenience, the water beyond what's needed to hydrate the cement. And that liquid water is mixed up in this chemical soup of all the calcium hydroxide, the calcium oxides, the sulfates, and all that kind of stuff that are being solvated in water are being brought up into a very concentrated layer on the surface of the concrete slab. That is again, a concentrated mixture of calcium and sodium and hydroxide and sulfide ions that sit on the surface. And as that bleed water evaporates, and if you don't work it back into the concrete over time, it's going to leave a salt deposit on the surface. Calcium hydroxide is going to get into its crystalline form. The sulfates will go into their crystalline form, all of which you might want to consider or call efflorescence. This is the white crystalline structure that you see on some concrete slabs. It's very brittle. You can take your razor and scrape off the surface of it. But this is what's coming out of the evaporation process of that bleed water that shows on the surface. If you allow the concrete its normal time to cure, what's going to happen to that chemical, the calcium hydroxides that are on the surface of the concrete slab? Over time, they're going to react with the carbon dioxide in the air, and they're going to carbonate. And as that calcium hydroxide reacts with the CO2 in the air, it becomes calcium carbonate. So that's kind of why a concrete slab will change color a little bit over time, from greenish looking material to a little bit more paler, a whiter thing, because calcium carbonate is white. How many of you remember back in your youth, in your physical science classes, of doing this test where you created a solution of calcium hydroxide in water and then blew through a straw into that and saw it change color. That's what we talked about. That change of color was result of the reaction of the CO2 in your breath, the calcium hydroxide in the water, creating calcium carbonate as a flocculent solution that created the white color that you're getting in that effect. So that's helpful for us as a floor covering installer to allow a concrete slab to carbonate, and that there is a considerable difference in solubility in water. Calcium carbonate is not that soluble in water. Calcium hydroxide is extremely soluble in water. I would rather be working on something that is not soluble when I'm putting water-based adhesive on top of it rather than something that is extremely soluble in that. That carbonization process typically will decrease the pH of a concrete slab, which is sometimes up to 14, down to a livable range of 9 to 11 in terms of pH. I will unfortunately tell you this is a slow process, and it will take some time. As you see here on the left side of the screen, that rate is about 0.039 inches per year in high quality concrete with a low water cement ratio. That number may change. If you've got a higher water to cement ratio, there's more calcium hydroxide on the surface and so on. But this is something that takes time, and it's why we would highly recommend you wait a little bit of time before you get on the concrete with water-based adhesives, and not just say, okay, it's been down there for 5 days, let's put a PSA adhesive, install LVT on it. It's not necessarily the great idea. So what is the chemical nature of this concrete surface? If you're not getting the overall picture of it right now, it is a complex combination of water-soluble inorganic chemical compounds and salts that can create instability in water-based adhesives, and some create this moisture problems where you might not think anything previously existed. It is not a rock. Sorry, even that's simple, so silly. I shouldn't be saying that. We know that concrete is not rock, but it's something that is soluble, and that solubility is going to create some problems for us downstream if we're not careful. So, what is all this talk about soluble salt deposits on the concrete slab, and why do I care about it being a floor covering installer? I did my pH test, I did my calcium chloride test, I did my RH test, everything's fine. Why can't I just go ahead and install floor covering and not worry about anything going down the road? The problem with that is that these salts are what we call hygroscopic. They absorb moisture. A common example of this is salt that we all know about. Anybody know why people put rice in their salt shakers on restaurant tables or outside picnic tables? It's because the salt without the rice absorb moisture and will start clumping up. It'll actually get to be a solid block of salt because it's going to continue to absorb moisture from the air. Well, the rice acts as a desiccant. It sucks up the air, it sucks up the humidity and keeps it from getting into the salt. So that's why people put salt in the rice to help keep it dry. I'll give you another example to think about. The calcium chloride test in itself is a salt, and we put it on an open petri dish on a concrete slab, and it's sucking humidity out of the water to the point where, out of the atmosphere, the humidity, to the point where you actually, some people have seen these calcium chloride kits look wet inside. There's enough water from the concrete that's evaporating with these 25-pound slabs. It's actually going to make that calcium chloride soup. Well, the same thing that we talked about with the salt shaker and a calcium chloride test is happening on top of a concrete slab because of this soluble salt soup that's on the surface. It can come from excess bleed water, it can come from too much water in the mix, it can come from topically applied densifiers and other soluble materials that can add to the overall salt concentration on the top of the concrete slab. So what's so bad about that? Well, as we mentioned, these salt solutions are hygroscopic. And when they come in contact with vapor or moisture, they're going to solvate, and they're going to create a higher concentration of solution on a very low concentration of solution below it. So I'm sorry, I'm going to try to explain this again. If I have a high concentration of salt on the concrete surface, it's going to want to pull moisture out of the concrete below it in an attempt to solvate itself, to make things equal. One of the common laws of physics is that everything wants to be at balance. It's the laws of entropy. This is the laws of solutions here. They want to be equal. If you put a semi-permeable membrane between a low concentration and a high concentration, laws of physics, the laws of chemistry are going to tell you that the low concentration side is going to move through that membrane in an attempt to make that an equal balance. But if it can't go back through, you're going to wind up pumping liquid through that membrane, creating what we would call an osmotic equivalent point. So again, how does this all relate to the surface of a concrete slab? You'll notice in these little illustrations that I have this in the glass box. There's no way for the liquid to evaporate on one side, and it builds up on the right side. On a concrete slab that's open, if you've got a high salt concentration on the surface, this process is working, but you're not seeing it because the water is coming up from the concrete slab, blending in with a high salt concentration, and then evaporating into the atmosphere. So you kind of have a built-in drying compound on the surface of the concrete slab that's working just fine on its own, pulling moisture out of the concrete, evaporating the outside, and leaving this high concentration of salt on the surface. Okay, that's what I would call that salt pump. But when I put an impervious moisture vapor barrier on top of it in the form of a vinyl sheet flooring or an LVT or something like that, I blocked the evaporation process. The liquid that was being pulled from the concrete slab mixing with that salt concentration that was happily evaporating and not creating any problems is now can't evaporate, but the process still goes on. So that high concentration of salt compound on the top layer of the surface of concrete slab is sucking moisture out of the concrete below it in an attempt to equilibrate itself. Again, the vapor will move back and forth, but the salt solution can't go back down. But since it can't go back down, it still keeps sucking water up. And this is where you get that saturated salt solution coming up underneath and building up underneath your impervious floor covering. This happens under epoxy coatings, this happens after sheet vinyl, LVT, or so on and so forth, where you've stopped the process of evaporation, but osmosis is still going, and you wind up creating this gooey layer of material underneath there. That salt pump generation of liquid is a solution full of calcium hydroxide, it's the sulfates and all sorts of stuff that are going to be detrimental to the adhesives, patching compounds, and in some respects even the flooring material. This is something that is a big problem, and this is, in my opinion, what's happening when you pull up a piece of sheet vinyl and you see soup under the floor. My hypothesis is 9 times out of 10 that was the direct result of a salted slab that had a high concentration of some sort of salt contaminant on the surface of it, creating an osmotic action, the salt pump sucking liquid up out of the concrete slab, creating this high pH solution, dissolving the adhesive, hydrolyzing everything, creating a massive problem for us. Again, that's what we're talking about here, the high pH liquid. This can even create enough pressure that it will create under epoxy membranes this classic picture you've seen where a guy's poking a knife in a sheet vinyl floor and you get water spraying out. Well, that's not water. It's a solution of chemicals, and it certainly wouldn't want something to get on you. You need to make sure you avoid doing that. But it's a chemical solution that builds up enough pressure to blister epoxy coatings, resilient floor covering installed with epoxy floor covering with epoxy adhesives or even PSAs or hard set acrylics. It can do all sorts of really bad things to you. So how do we know if a slab is salted? It's really not something you can see visually, and it's not something you're going to find out with doing moisture vapor emission rates or RH tests. The pH test will provide some insight. Again, keep in mind that the pH test only measures remaining hydroxyl stuff, which is the calcium hydroxide portion of it, but doesn't give you any idea of what concentrations there might be of sulfate ions or chloride ions or sodium ions or calcium ions, the other kinds of things that are going to be hygroscopic and absorb moisture over time and create these kind of problems for you. Ideally, the best way to do this, and no one really wants to hear this, me talk to you about this, but petrographic analysis of a concrete slab is really a good idea to do. And here's an example on the right side of your screen of a petrographic analysis of a concrete slab, where the people doing the analysis threw up some yellow flags, red flags that said, on this particular sample, the first 1/8 of an inch of material had very high levels of sodium and potassium against the normal numbers. Again, you can see 3 millimeters below, it goes to 130 to 240 parts per million versus something that's almost 10 to 20 times higher on the surface. This is the kind of stuff that should raise your spider sense and make all your feelers go off and say, I might have a problem if I install over a concrete slab that has a high level of these kinds of materials on the surface, whether it's a high pH or a high sodium or high potassium concentration. These are the kinds of things that are going to initiate this salt pump action on a concrete slab, causing it to have an impact on the adhesive performance, pulling moisture up on the floor, creating liquid underneath the floor, all sorts of bad stuff that's going on. So there are a variety of services out there in the marketplace that can help you understand this stuff, but it's something I'd highly recommend at least taking a look at in some cases. Unfortunately, we oftentimes go to core samples when we're trying to analyze a problem. What happened? Why did this floor blow up? My calcium chloride numbers were good. My RH numbers were good. My pH numbers were okay. Everything looked fine. Why did it still blow? This is 9 times out of 10 the reason why that happens. So I want to wrap this up. I appreciate your guys' time here, but let's just in summary, remember that concrete may look and feel like stone. It's hard, it's durable, it lasts forever, but it is made from a magical complex chemical reaction that does leave stuff on the surface that is soluble. Calcium hydroxides, calcium oxides, sodium chlorides, calcium chlorides, and so on and so forth. It's those soluble compounds that impact the performance of adhesives and can be the precursors to this salt pump osmotic activity that can create all sorts of problems for you. pH testing, although it's good, is only going to test the amount of free hydrogen ions or free hydroxyl ions, which is indicative of how early the concrete is, how much calcium hydroxide is on the surface, and so on. But it doesn't tell you anything about that other chemical soup, which we already know that's in there based on what's going into the concrete mix to begin with. Again, moisture testing is also important. It pretty much tells you the potential for feeding the salt engine. Osmosis is going to keep going. These salt pumps are going to keep functioning as long as there's moisture to pull from. So a highly moist concrete slab that's the 99% level is like saying that I got a really deep pool of water and this salt engine's, I got a full tank of gas and it's going to run for 540 miles. As opposed to something that's a little bit drier, the moisture testing numbers is 75% and RH and maybe 3 pounds of moisture vapor emission, or the tank is quarter full, then it's not going to be a problem. So again, high moisture content concrete slabs, high salt concentrations on the surface are huge potentials for the salt pump activity and really dangerous for the stability of water-based adhesives. And again, when adhesives look like soup under the flooring material, most likely it's because of this salted slab. And the only way to fix these kind of problems from happening again, you can't just scrape off the glue and reinstall. You really need to remove the top layer of the cement, the concrete, remove that concentrated salt level, get to something that's a more normal thing, and get on with your life, and that will help stop the osmotic reaction. Again, there are companies out there that can do petrographic analysis. I've recently discovered a new tool that might help you. It's called the Defelsco Positector Soluble Salt Tester from a company called Hold Tight. If you're interested in that link, I can help you with that. That's the kind of tool that will help determine whether you've got ridiculously high levels of sodium, potassium, sulfates, and chlorides. I would start putting that or looking into that as a toolkit to add to your box of tricks to analyzing a concrete slab. Because I think really, in my opinion, that's one of the more important things to look at is that salt concentration that's on the surface of concrete slab. And with that, I will turn it back to Jen and open the floor up for any kind of questions that might be there.
Awesome. Thank you, Jeff. And yes, we do. We have questions. So the first one, is there any correlation between in situ probe and calcium chloride testing results?
No. Now, as I've mentioned before, they measure two completely different things. One is a measurement of the rate at which something is evaporating. So it's like, how fast am I driving down the road? The other one is a measurement of the state. What is the current state, or how much gas do I have in the tank, right? For analogies, those are two different things altogether. One is a rate of evaporation, and the other one is how much moisture is in the slab.
That's
So
a
those
good
two do not
analogy.
relate.
Yep, that's a good way to look at it. Okay, so assuming all slabs have varying levels of unreacted Portland, how does that affect the MVER?
Well, it's going to be the thing, the unreacted Portland cement base that's still in the concrete is going to continue to pull some moisture out of the slab and continue to hydrate. That's why concrete gets stronger and stronger and stronger over time as it continues to pull moisture out of the concrete slab. But there's only a limit to how much moisture the Portland cement can actually pull out of it. Again, it's a chemical equation. I think I've called this before stoichiometry. It's like 2 moles of hydrogen, 1 mole of oxygen create 1 mole of water. It's a very defined limit. So there's only so much of the water in a concrete slab that is available to react, where the rest of it was added, as I mentioned, as water of convenience, water to placement. So, the unreacted cement left in the mix is going to continue to pull moisture out of the concrete slab. It will have a negative impact on some of the values, probably more so on the RH than would be on the rate of evaporation. The rate numbers, in my opinion, are very indicative of the water to cement ratio. The higher the water to cement ratio, the more water you put into the mix, the more porous it's going to be. So it's like opening the valve up on the evaporation rate machine. If you have big gaps and big holes and a lot of surface area, it's going to evaporate a lot faster than a tighter concrete slab. So if you've got a lower water to cement ratio below the 0.45 or 0.4, first of all, it's going to be a bitch to place. It's going to be very stiff, but the porosity is going to be considerably less, and your moisture vapor emission rates will decrease by that. I've seen concrete slabs that have moisture vapor emission rates less than 3 pounds, 2.5, even 1.7 pounds for rate leaving it, but the RH levels are 99%. You got to wonder, how is that even possible? Well, because one case, that slab was highly burnished. had a little bit of fly ash into it, which kept it non-porous virtually on the surface. So if it's all non-porous, there's no evaporation rate and there's no MVER. But that means all the moisture is captured inside the slab, and that's why the RH levels are so high.
Makes sense. All right. Another question. Will the water from taking a core sample reduce or skew the surface findings?
No, because what you're not measuring water on a petrographic analysis, you're measuring ionic composition or the amount of elemental presence, the amount of sodium elements, the amount of potassium elements itself. This test is, I wish I knew more about it, but it's very specific to the elements that are left on the surface or ions that are on the surface. So it's like doing an FTIR or some sort of a chemical test that reads out a percentage of sodium ions on the surface. It doesn't really have anything to do with the water that's there. So that doesn't really impact it. What you're looking for is the residual ionic material on the surface, not necessarily the water. The water will actually get in the way of some of these test results. You want it gone anyway.
Yep. Okay. When not knowing the depth of the existing slab, what depth would you recommend drilling the probes?
I'm not going to make that recommendation.
That's
That's a good question. I'm sorry,
yeah,
you need to find out. You're going to have
yeah.
to, I can't.
That depends on the each case. Wow.
Yeah. The
Yeah.
answer to that is you need to find out.
Yeah, exactly.
Sorry.
That's a case by case basis.
Mm.
Yeah. Okay, new question. Can we apply polyurethane on new concrete after about a week so we can keep the substrate from dust, which we should remove later before applying the coat? Okay, that I guess the question is, can we apply polyurethane on the new concrete after about a week?
All right, so generally speaking, urethanes are not going to be affected too
Yeah.
much by high pH conditions. In my opinion, the better solution would be to use an epoxy material, which, like our Planasil VS material, is designed for use over concrete slabs that are high pH up to 14. These are the kinds of materials that I would consider flooring expediters. If you do want to get on a concrete floor, need to get on a concrete floor to install floor covering 5 days after it's placed, God only knows how many that works. I mean, I hear that all the time. I need to pour a slab and I've got to install floor covering 5 days later. The safest, the smartest way to do that is to use an epoxy on the surface, which doesn't care whether it's a high pH, covered with a primer and a leveler, which is porous, and you put an adhesive on as well. Would I use a urethane on that slab? That's a question. I think Planasil PMB probably would work on that situation. It's going to react with the free moisture on the concrete slab. Again, it's not terribly impacted by the pH of the system. But in terms of using a urethane, would you take it off later?
Yeah, I'm not understanding that part of the question. Remove it later before applying the coat.
What I might suggest, and I don't really know if this makes sense, but you could help speed along the carbonization process by opening up a case of Pellegrino and pouring it all across the floor, which is carbonic acid, if you will. And that carbonic acid is going to react with the sodium hydroxide and help along with the carbonization of the process, or open up a CO2 fire extinguisher that concentrates some CO2 on the surface that might lower the pH as well. Even using carbonic acid is potential, but you need, once you do the acid treatment of a high pH concrete slab, you need to rinse it often to get rid of any excess hydrogen ions that can be a problem as well. So you don't want to have anything left that's solid. You just want the calcium carbonate left on the surface, not anything else. Okay.
Yeah. All right. if you want to follow up with that second part of that question, please feel free to type it in the Q&A box there and we'll tackle it. But another question, are there any tests for salt ions on the concrete slab, like the pH test? I think we've discussed that one.
Yeah, that one. Okay,
Yeah.
I think that was what I mentioned before about this,
Yep.
the hold tight. And just
Yep,
type it,
exactly.
holdtight.com. Take a look at that. Might be
Yeah,
a great tool for you to use to start.
they're a great resource, holdtight.com, and the pause detector tests. Really, really
Yeah,
great
it's just
resource of.
for the sake of this discussion, the people who are involved in epoxy coatings, going on top of concrete slabs, have to deal with this all the time. There are numerous articles written about osmotic blistering underneath epoxy coatings. And epoxy coatings have the same thing in common that an impervious floor covering does. They're an impervious moisture barrier. They block the evaporation that's going on a salted concrete slab. And when you block that action, when you block the evaporation, the osmotic action has no other choice but to build pressure and blow blisters off the floor. So something
Yep.
to look at. And they've learned more about it than we have. That's why I'm trying to pass this information along.
Yeah, it's it's quite an industry, the floor covering industry. Let's see, where do I go to get petrographic analysis of concrete slabs?
Well, the first thing, the easiest thing to do is look for Petrographic lab near you. They're all very common and very available. A lot of concrete testing is done everywhere. MAPEI has the ability to do some of that for you as well. I don't say that I don't want to be inundated at the lab with a bunch of core samples, but we can certainly help you look at that. And we have the capability of doing that kind of analysis and have done it in the past. Okay.
Fantastic. All right. Well, you know that if you're like me, then when the second this thing ends, I always think of 12 more questions. So if that happens after we say goodbye, please do send the questions to MAPEI Digital at mapei.com, and we'll be sure to forward them on to Jeff. But we do want to thank you very, very much for taking some time out of your busy days to spend with us. We know that time is very valuable, and we thank you for spending a little bit of it here. And with that, I will go ahead and say goodbye. And thank you, Jeff, very much for a very wonderful presentation. I know I learned an awful lot. And this has been recorded, and we will be putting it online on our website. So if you want to revisit and learn more, it'll be there in a few weeks, probably, for you to enjoy again. All right.
Okay.
So
Yep.
with that, thank you, everybody. We'll see you next time.